Hello, everyone. Thank you for present a new HTN approach. I hope it will be helpful for you. My name is Kosuke Namiki. I'm a senior AI engineer at Square Enix. I've worked for Square Enix since 2012. Tomohiro Mori is an AI engineer. He's today's co-speaker. He implemented major part of our system. Let's start. In the game industry today, there are a lot of choice of game AI system. The oldest and most widely used is the finite state machine. Finite state machine is a very reactive system and has been mostly favored in controlling action games. Behavior trees are categorized as a reactive AI system, but they are suitable for writing behaviors that are slightly longer term than FSM. It also has advantage of being easier to manage because the number of state transitions is more limited than FSM. GOAP is a decision-making system with a planning function for writing long-term actions. It can create rational action plans through simple state search, but it has a weakness that it can only generate relatively simple action chains because it doesn't have hierarchy. HTN is known to be the best choice of game system for writing long-term behavior in general. It has the advantage of hierarchical tasks so that relatively complex actions can be included in the plan. Recent game AI has excelled in immediate response. You can create a smart responsive AI with FSM or behavior tree. However, it tends to lack the ability to perform actions with long-term perspective. How to achieve long-term and smart behavior is a major challenge for today's game AI. To start off, what is HTN? HTN stands for Hierarchical Task Network. To put it simply, HTN is a traditional planning method for AI. It has been used for planning in a static domain. A lot of game engineers have some base expectation for HTN. In general, it is expected to be able to predict future situations and take deliberate action. Here, I'll show you an example of HTN. There are two types of tasks in HTN. Primitive, which is a one-action task, and compound, which consists of a lot of smaller subtasks. One of the major functions of HTN is the decompose function. It allows the HTN to break down a compound task into multiple tasks, allowing you to solve the problem. Then we have the hierarchical planning. It allows the HTN to break down a large problem into sub-problems so that it can solve more complex plans that non-hierarchical planner like slips. I'd like to mention recent game industry around HTN. Real-time games increase in console market more than a decade. Game situation changes in real time. HTN is good at planning in a static environment, but it's not designed for a dynamic environment. For example, in the problem of stacking blocks in order, it is difficult to deal with an event such as an earthquake that chases the blocks to collapse. Player behavior is unpredictable to HTN. It's like stacking blocks on a rocking boat. HTN is unable to incorporate uncertain environmental changes into its planning. The problem of uncertainty in HTN. In HTN, after the planning phase is over, tasks are arranged in a chain and executed in sequence. Once a task chain is created, HTN can't modify that. If the environment changes, the existing plan is discarded and a new plan is recreated by replanning. For example, an AI is executing planned tasks in sequence. But the environment has changed. The AI will discard all remaining tasks and recreate them by replanning. The more frequent the replanning, the less able the AI will be to think long term, and the more it will turn into a reactive AI with a narrow view. In order to adapt to change in the environment, various techniques such as Reggie evaluation have been devised. However, the fundamental problem is that HTN has failed to incorporate uncertain environmental changes into its planning. This is a shortcoming of the algorithm itself and can't be solved by adding new features. We wondered if we could address this uncertainty by improving the HTN planning process itself. Now, I should say, plans are nothing. Planning is everything. It doesn't matter how many plans you have that can't adapt to situation changes. Instead, generating adaptive plans with robustness against situation changes is very, very important for real-time game. From here, I'd like to present a new approach at HTN. Our motivation. Even though various situation changes in real time, we want to achieve more long-term behavior with planning. To take advantage of planning, we want to minimize the number of replanning as much as possible. Instead of symbolic planning, we want to make planning more relevant to the game situation by using simulator. Other approach is called the Advanced Real-Time HTN or ART-HTN for short. We have three main features to our system. First, we have the multi-scenario plan. Our planner should have multiple scenarios in order to handle uncertain situation change. Next, the simplified simulation planner. We assumed that a game simulation would be more appropriate than symbolic planner. Better planner might reduce the amount of replanning. Lastly, the executor. Part of the role separation between planning and execution. We think that plan needs to be open to modify even after it's created. By giving more authority to the executor of the plan rather than the creator of the plan, we thought we could operate the plan flexibly. Let's look into the first feature, multi-scenario plan. Starting with the multi-scenario plan, the main point is the reusing of temporal states. Traditional planner discards temporal states in search phase and returns only a final task chain of plan. But temporal states can be used as subplans. Our multi-scenario planner returns a plan with multiple branches. Planner leaves branches in the middle state of search whenever possible. Here you can see the multi-scenario plan in action. As you can see, it is made up of tasks and situations. Situation is a simplified model of game world. It has all simplified data in game world. For example, character's position, hit point, and internal conditions such as state ID or hostile AI agent. Situation has links to previous and next situations, so situation form a graph. We call this graph situation task network or ST network for short. Then we have the different types of tasks in our system. We are still in the process of verifying, so we don't have a lot of covered yet. There are two main kinds of tasks, primitive and composite. Primitive task is a simple action task which has precondition and simulate function. Composite task is a more complex task. we have two basic types for it currently. One is the FSM task. To simulate opponent behavior, our planner can use FSM in planning phase. FSM can be used as a model of opponent behavior. Step task. It's a very simple FSM. It's almost like a sequence node of behavior tree, but step task can have simple loops or small number of branches. They can describe directional actions with start and end states with step task. Next, we move on the simplified simulation planner. First, the planner generates ST network with a simple simulator that runs on height map. This animated image on the left shows an example of a plan generated by the simulator. When the decision maker can choose its action, it expands the terminal situation node and creates multiple branches. Enemy model generate branches at a certain probability when they change their behavior. Here is the flow of task assigning. To expand the terminal situation node, decision maker chooses a task for every character. Decision maker can assign primitive task when its precondition matches to the situation. And decision maker can expand composite task when the node allows. In this case, composite node create multiple copies instance and modify internal state ID. Here is examples of expansion of composite task. Then FSM has transition to state ABC. The FSM task can be expanded to ABC copied instance. All data in FSM copied after that, the task executes state transition to make ABC versions of task instance. Every agent decision maker can conduct such process. So total amount of situation nodes tend to become huge. To reduce ST network size, expand function receive expand threshold. The task can be expanded only when the random number exceeds this threshold. From here, I turn over to Mori, who was in charge of the implementation.
Hi, my name is Tomohiro Mori. Let's take a look at the last function, executor. To begin with, the ST network will allows us to determine which task is best to choose in which situation. However, take only data in the planner and cannot be executed in the game environment as is. For the execution, we have our executor decomposing tasks into operators. First, the executor will look through the situation branches and choose a task with a high evaluation among the children, which conditions similar to the current situation and transition to it. The task is then decomposed into operators and executed. Now, I can say, planning is nothing, execution is everything. Our executor is able to choose best plan from ST network and modify that to execute in game world to achieve long-term behavior. From here, I would like to show you a demo of our system. First demo is reach shooting. Reach shooting is a popular tactic used by tanks. In our case, it involves using the heel to shield the lower part of the neck. To detect heel from terrain, I use simple counter line algorithm. Detect counter line from terrain with fixed height intervals, and find orientation and distribution of heels by principal component analysis. This method is rough granularity, but fast algorithm for simulation. At first, I want to show simple version demo. This means AI simple task to fight and he can't find any hills and obstacles. He tried to fight without using any obstacles. You can see his executed internal states on upper left debug window. Now he chooses charge attack operator. Charge is a very brave action, but it takes a lot of risk. So he is taking a lot of bullet. Finally, he was defeated. Next, I want to show reach shooting version demo. I added reach shooting task to our planner. Our LTHD is able to compare charge task and reach shooting task and then chooses best one. Now, AI can find hills and calculate best firing position using reach shooting task. He is able to fight with using obstacles. He reached the firing position and start aiming. The enemy bullets are not hitting him as hard as before. And the enemy's entire body is exposed to his gun. The difference in projectile area against the gun is directly reflected in the hit rate. Finally, we won. Then, our final demo. The reconnaissance in force. In this demo, our mech has multiple objectives. At first, he will try to detect enemy main force and eliminate weak target. But if he predicts a risky situation, he tries to retreat. If he can't retreat, he will use powerful weapon to destroy or make enemy give up the chase. The AI is activated and beginning to search for enemies. When he found a weak target, he will attack and destroy it. The executor is running a patrol operator, which consists of reconnaissance actions. After that, he has found it. Now he is searching the enemies with his main camera. Oh, he has found a strong enemy that has red color and seems to come from the head. The AI planner decides whether to actively engage or passively retreat. This time, the strategy of using a smoke screen to retreat has been selected. Since he couldn't escape even with the smoke screen, he will fight with all Since he couldn't escape even with the smoke screen, he will fight with all ammunition he has. All bullets, he adds missiles at the last resort. And well done, he has defeated the enemy. To achieve long-term behavior in dynamic environment, HDN system should be improved. We present at HDN approach which consists of 3 features: multi-scenario planner, simulation planner, and executor. We verify that on our real-time demo with dynamic environment. That's it for this session. Thank you for watching. By the way, we have another session in GDC 21. If you are interested, please see our animation session from design, pre-procedure animations for Makes. If you have any questions, please let us know, or please send questions to our mail. Thank you very much.